Okay. We will take on the next example problem. This one has to do with a very common idea. Anybody that has played a sport, either a racket sport or cricket, would understand the concept of a sweet spot. I am sure you hear commentators on TV talk about what is a sweet spot. That is basically the point on a body. Let us say I have a racket and there is a point on this racket at which if I hit the ball, the effort involved in holding the racket is very small. We will talk about more quantitative ways of understanding this. So, in other words, there is one point at which the effort involved is small and there are points around it where the effort involved increases as you go away from this point. Okay, so let us take a very simple example to start with and understand this idea called the center of percussion. Okay. The problem involves a long rod which is fixed on an axle at a point A. The center of mass of the rod is 3 meters away, since the rod is a total length of 6 meters, and a force 36 newtons acts at a point D. Okay. D from the far end of the rod, and the weight of the rod is some 96 newtons. Okay, we want to understand the reaction forces felt at A due to the act of this 36 Newton force acting on the rod. Okay. So, let us do that, and then we also need to find the distance D such that the tangential axle reaction will be 0. Okay. So, let us see how to solve this problem. In order to be general to start with, I am going to use the force this 36, I am going to replace the 36 Newton force with a symbol capital F, and we are going to try to solve this problem in terms of F and D. Okay. So, let us take that first. The first simplest point I want to bring to your notice is that the only part that matters for the kinematics is the distance from A to G. So, if this is rotating at an angular velocity omega and has an angular acceleration alpha, and if the length 2L is 6 meters, the total length is 6 meters, then this length AG equal to L, which is 3 meters, which means from the fixed point A, the acceleration of G has two parts. There is a tangential acceleration AT, which is a magnitude L times alpha, which is equal to 3 times alpha, and there is a normal acceleration A n, which is L omega squared. So, this is what the kinematics tells us, that we are able to relate the angular motion omega and alpha to linear accelerations in the tangential and normal sense. Okay. So, now let us go on and draw a free body diagram of the rod. We have to first understand that gravity is going into the plane of the board. So, we have G, and at this point there is a normal reaction and a tangential reaction. A force F is acting a distance D from the end of the rod. Okay, we have the tangential acceleration AT that we decided earlier, a normal acceleration AN, omega and alpha. So, the only forces acting on this rod AGB, I will denote the end of the rod as some B, is a force F acting at a distance d from the end B, and two reactions, the normal reaction RT and the normal reaction Rn, and a tangential reaction at the pivot A, which is magnitude RT. Okay, so what do we learn from this? So the first thing we will do is apply our force balance. So if I take all normal reactions towards A to be positive, sum of all normal forces is mass times the normal acceleration. What we find is that Rn equals m times An, which also implies Rn equals ml omega squared, where omega is the instantaneous angular velocity. Okay, so now let us take on tangential force balance. Sum of all tangential forces is mass times tangential acceleration. The only tangential force acting on this whole rod, with tangential meaning tangential to the motion or perpendicular to the rod, RT equals mass times tangential acceleration. F plus RT equals mass times tangential acceleration. RT is not the only tangential force, there is F as well. So, F plus RT equals ml alpha. Then the last equation we have has to do with the idea that if I say counterclockwise moments positive, moments about G equals Ig times alpha. So, the forces that cause moments about G are RT and F. RT causes a moment, F causes a moment, no other force causes a moment about G. So, RT times L causes a clockwise moment. So, in this sense that takes on a negative sign. F on the other hand causes a counterclockwise moment. So, F times L minus D equals Ig, which in this case is ml squared over 12 times alpha. So, let me rewrite this second equation, minus RT plus F times 1 minus D over L equals ml squared. Now, we have to be careful with the L part here. The angular momentum of the rod is m capital L squared over 12. L is the total length of the rod. So, in this case that would be m times 2L squared over 12 times alpha. So, minus RT plus F times L over D gives me ml alpha over 3. F is a known quantity. I have two equations here. I will call this 2, I will call this 1, and this is equation 3. I can solve 2 and 3 to find what alpha would be and the corresponding L and the corresponding R sub t. So, if I simply add 2 and 3, what do I have? F plus F into 1 minus D over L equals ml alpha plus ml alpha over 3. So, it implies F times 2 minus d over L equals m L alpha 4/3 m L alpha, which also implies alpha is 3 F over 4 m L times 2 minus d over L. Okay, this is the angular acceleration that the rod sees. So, now solving for r sub t, I can take any one of these equations. I will take equation number 2 that says F plus r t equals m L alpha, which implies F plus r t equals 3 F over 4 times 2 minus d over L. Which implies R t equals 3 F over 4 times 2 minus d over L minus F. So, this is 3 F over 4 times 2 is 3 F over 2 minus F is half minus d over L. Okay. So, R t, let me write this, R t is F times half minus d over L. So, let us go back to our rod. This is the pivot A. There is the center of mass, there is the end point B, and there is a force F acting at a distance d. Now, at this point there is a normal reaction and a tangential reaction. The tangential reaction R t scales with the value of F. So, higher the value of F, the higher the value of R t, except that you have this constant of proportionality between R t and F, which is half minus d over L. So, let us say if I ask the question, what happens if d equals L over 2, that is, if this acts exactly L over 2 from G and from B, what happens? The answer is R t is 0. Not just that R t is 0, R t does not depend on F. Isn't that even more surprising? The fact that R t is 0 means that the pivot A does not feel the effect of a force being applied at this point. I will call this C just for the sake of referring to it. So, I do not feel any magnitude force acting at this one particular point C in the reaction forces at A. So, in fact, if you notice, remember there is also an R n, and that R n is simply m L omega squared. Okay, so, if this rod is rotating in an angular sense with an angular velocity instantaneously of omega magnitude, R n, which is the force required to hold the rod at pivot A, simply scales as m L omega squared. That is our centripetal force, or that is the force needed to hold on to the rod in a rotating configuration. R t, however, does not depend on F, which also means that R t, the effect of F is not felt at R t. Okay, so, now this F can be of any nature. meaning f can be a function of time. So, let us say if I have f is 0 at a particular instant, there is a force F felt and it goes back to being 0, but this force is felt at this particular point C. Is the motion of the rod affected by the action of this force F? It is affected, since the acceleration depends on F, okay, even if d is L over 2. So, the angular acceleration depends on F, but not r sub t. So, what does this mean? If I was a batsman, if I was holding this bat at a particular point, and if a ball came and hit the bat at this particular point, a distance L over t from the end, L over 2 from the end, then the force I would feel here would not depend on the fact that there was a force, the reaction force in my hand here does not depend on whether a force appeared at this point O or not, at this point where the ball hit the racket or not. So, in other words, if the ball exactly hit this point, I would not feel the ball hitting my racket or cricket bat at all. That is what we usually refer to as the sweet spot. Now, for a rod of uniform radius, it is at a distance L over 2 from the end. So, if you were, let us say, a baseball player where the rod is kind of designed to be of a uniform radius, the distance from the edge where the ball hitting would not be felt by the palm, by the person holding, would be a distance L over 2 from the end. For any other shape of this bat, let us say a cricket bat or a tennis racket, this actual position of the sweet spot would be different from it would not be L over 2, it would depend on the actual moment of inertia formula of this body about its own center of mass. But you would certainly have a point at which the moment of inertia, at which the tangential reaction, which is basically saying if I was holding the bat, a force in my hand that would cause the racket to turn like that would be nearly 0. Okay. So, a force acting here would not be felt in a tangential sense here. All I would feel is the force necessary to swing the bat in the first place. In order to swing the bat in the first place, I need to hold on to the bat and cause it to move in a rotating sense. That would require a force ml omega squared naturally. That is just the force needed to hold on to a bat. So, even in the instance of the ball hitting the bat, that is the only force I still need to hold on, I still need to exert if the ball hit the sweet spot exactly. Now, anybody that is a sportsman that has hit a hard ball, whether it is a tennis ball or cricket ball, would know this, that there is a particular point at which your racket would not turn in your palm essentially. That is, any kind of a turning action in your palm has to do with a tangential reaction force that is unbalanced in your palm, whereas if the ball exactly hits the sweet spot, there would be no unbalanced tangential force, which would mean you would only need the normal reaction force to hold on to the racket. Okay. So, now let us go back and see what happens if I hit the ball near the sweet spot, not exactly at the point, but near the sweet spot. Okay, what I do know is that for this particular rod, which is a nice simplified formula, simplified model of either a cricket ball or a baseball, cricket bat or a baseball bat, if I now plotted the tangential reaction as a function of the point where the force acted. So, at this point, which is, if this is B, if the force acted at the very end, which would mean D is 0, RT would be F over 2 positive. Okay. And at this point the tangential force goes to 0, and if D is L, then I would go to F being minus F over 2, and then if D is 3L over 2, the force would be almost twice F. So, this is a distance L, this is L over 2, this is another L over 2. So, at this point L over 2, which is 3L over 2 from the end A, the tangential reaction goes to 0. If the tangential reaction is not exactly at this point, but slightly off to the side, you would feel the racket. If it is slightly away from you, you would feel the reaction force to be positive. That means the racket is going to have, you would have to push the racket forward in order to hold on to it. If it is closer towards you, you would have to pull the racket towards you in order to hold on to it. But the point here is that it only goes linearly with variation around that D equals L over 2. So, small changes in D away from L over 2, that position A or that position C, will only cause small deviations in the tangential reaction force, only linearly scaling with F. Okay. So, I hope this illustrated the whole idea of a center of percussion and the fact that sporting equipments have a sweet spot, that any kind of an angular movement is and a force acting instantaneously is not translated to the palm. Now, in a real cricketing situation, the body, the rigid bodies under motion is essentially a 3-piece assembly. So, there is a shoulder joint, which is, you could imagine, is fixed, then there is an elbow at which you would probably have some movement, but if the elbow is rigid, you would have some wrist action coming in. Similar, so and if the force acts somewhere on the bat, which is further down here, you could extend this same calculation, albeit slightly more complicated, because this would involve more than 1 degree of freedom, but other than that you would still be able to calculate a point of action of the force at which the tangential reaction at your shoulder is 0. Okay. I hope this illustrated the point. We will try to take this further in the next set of examples.